right, so let's look at effective mass measurements. So we're really after trying to validate the theories and characterize materials properly. Important things to remember here again, full bands do not conduct because the electrons have no spaces to go. Empty bands do not conduct because there are no electrons that can go around. So again, typically in a typical semiconductor that has some doping, we have electrons that are here in the conduction band, and we have holes or lack of electrons here in the valence band. So ideally, we would like to measure the curvature of these bands. We are interested in the topmost valence band holes and the bottommost electron conduction band states. And we want to figure out the slope of these bands, and can we probe just the specific species of electrons and or holes. And we don't want to excite necessarily the carriers from one band to the other. We want to measure them as they are in their bands. So what are methodologies that can do that? Now, the fundamental approach is here that you can rotate electrons in the crystal with a magnetic field. All right, so imagine that you're at cold temperatures and electrons could circle around a externally magnetic field. So let's imagine this electron zooms around the magnetic field. And what would that look like in phase space, in the K space in the reciprocal lattice? So imagine you have an electron that starts out in this coordinate system and has a velocity kx0. So it propagates with a velocity like this. You would find the equivalent electron here in this kx space here. So it's rotated around. So now if you have the electron at this spot over here, it will have on the dispersion here in K space, it would show up here. Now, what you notice is that in this magnetic field, this electron can zoom around like a free particle as it could be in free space with a magnetic field. Now, this means it will probe an equi-energy surface. It will be on the energy of the electron doesn't change. It is rotating with a Lorentz force in a magnetic field. Now, so as it electron continues around, it also in phase space explores the whole K space as well. And it's a circular phase space like this, or it's going really around an energy constant surface. So that surface may not be spherical, as we will see later for materials like silicon and germanium, but in the simplest of cases, for say gallium arsenide, we can certainly imagine that to be the case. So here we are, this electron moving around in a circle in a magnetic field, and the projection of its momentum is shown on the right, and it's also on a spherical K space. So the electron in K space is moving in a circle, and it's moving in physical space as well in a circle. All right. Now, let's look at this 1D problem like this of a spherical dispersion. We have the Lorentz force acting on the electron, and we can calculate the velocity of the electron now as a function of the magnetic field. So here's the Lorentz force on the electron, and we can resolve this expression here for the velocity of the electron. All right, if we have the velocity of the electron, we have the time it takes for the electron to go around. So that's this tau, that is 2 pi r, so the circumference of the circle it takes over the velocity. We have the expression for the velocity, which plugs in right here, and we lose the r. Okay, so the r falls out of the expression, and if with 1 over tau, we have the frequency that the electron oscillates, and then we also have the angular frequency like this. So if we measure the frequency that the electron zooms around in a circle, we can then effectively measure the effective mass of the electron, given that we know the magnetic field. All right, So that really leads us to the measurement of the effective mass. So what you do is you shine a current, an RF current into the material. You apply a magnetic field in a specific direction, and you measure the current that comes out. And what happens is that as you measure the system at some specific magnetic field, you find a lot of absorption. So you couple the resonator from the outside signal, the resonating or rotating radiation, so to speak, to the natural resonance of these electrons in their specific bands on the equi-energy surfaces. Okay? So as these resonators couple, the electrons will stay excited. They will take on the energy of the radiating frequency, and you will measure less current coming out. So you have more current coming in than coming out, so that's the absorption, and you do that for a specific range of magnetic fields. You find a peak for one specific magnetic field, and you can find another one for a different magnetic field. And those can correspond to, say, a conduction band electron and to a valence band electron. And now you need to relate these resonances to specific masses. And you can do that with this expression here. Okay? Now, these expressions don't give you an exact answer as to which one is a conduction electron and which one is a valence band hole. So you might have to think a little harder on how to distinguish those. All right. Now, I wrote down here that this calculation or this measurement is relatively easy for spherical surfaces like gallium arsenide, or for holes where you can assume for low energy holes that the isosurfaces are spherical. Now, if you have a more complicated material like germanium or silicon, you know that you have multiple valleys in the conduction band. So here is the case for germanium, where we know we have 8 equivalent valleys. And if you imagine you shine light on this material, light, magnetic field radiation, now you apply a magnetic field and you let an RF current flow through the structure in a certain direction, you will ultimately have the electrons move around these equi-energy surfaces with the magnetic field. And there's a couple. So there is rotation around the short axis, and there's rotation around the long axis. So you expose in the same valley, in the same conduction band edge, you expose really multiple resonance frequencies, and you have to sort that out in an experimental structure. So you can clearly see that you have these 4 symmetry angles that are running through this crystal. You have these 8 valleys are aligned into 4 specific axes, and depending on which angle you shine, you have the magnetic field adjusted to, you will expose different circular motions around either just the long axis or purely the short axis, or a mixture thereof. And of course, you always have a mixture, but the components of the mixture depend on the angle of the magnetic field. So it gets a little bit more complicated. You can derive something called a cyclotron frequency, where you divide the rotation that you can have in the system along the long and the short axis, and any mixture thereof, into contributions that have to do with the angle theta that the magnetic field takes with these ellipsoids. So that has to do that really the Lorentz force is a 3-dimensional effect. So you can write F equals ma, where m is now a tensor, and also you can write down the vector field for the or vector force with the Lorentz force like this. and you can expand it out in a Cartesian coordinate. Now you really have a dependence of the projection of the velocity in x, y, and z as a function of the various magnetic fields and the velocities of the particles around these ellipsoids. Now, it gets a little bit messy. It's not too much of an algebra, but given that you have a certain angle with a magnetic field, you can really play around with this. And indeed, in experiments, people choose certain magnetic field directions that reduce the number of angles. So here, if you shine the magnetic field at a specific angle here of 110, you reduce the number of critical angles to 3, and people measure indeed 3 peaks for electrons that are being identified, and you can devise the effective mass of these 3 ellipsoids. And of course, you can also find other peaks that you can then begin to associate with holes. So with the 3 peaks in B1, B2, and the cyclotron mass derived by the magnetic field strength, you can get, with the angles, you can get the 3 different masses. So these are measurements that have been done quite a while ago. They have been done very carefully. And as I mentioned, you can derive the effective masses out of this. And you can do the same thing for the valence band. And in the past, I had mentioned that there's a light hole and a heavy hole, and they're considered to be spherical for small excitations. They will show up as peaks like these. So with this, you can really measure these effective masses through absorption experiments, and more recently, other researchers developed other methodologies like RPAs to map out band structure explicitly. With that, I'm just going to summarize these concepts of an effective mass and band gap, etc., can actually be physically measured and explored. And without such experiments, we really wouldn't have a validation of these theories. So this remains always a critical item, that as you develop theories and potential explanations, they're really driven by experimental evidence. And if the experimental evidence disagrees with the theory, you end up having to revise the theory. So that's the normal process in science. And this section here shows that band gaps and masses can be measured for real devices, and that is why they work well for real device design. So thank you very much.